It's time for the iconic first and last annual Greedy lecture. So, Greedy is famously hard to talk about for like lecture purposes because no Greedy problem is a monolith. They're all different. There's no like strategy or algorithm that works for every problem. But I'll talk about some Greedy problems. Hopefully I can, elucidate some through lines, some strategies that work on like a lot of them, some like similarities between them. And we'll see what happens, and it'll be awesome. And we're gonna start with sort of a classic, like boilerplate problem, sort of a basis that like problems can like build off of, and it is lex min slash max. So lexicographical min slash max. What does this mean? This means we have like, let's say like a set of strings, or like an evaluation function of a string, and we want to find the lexicographically minimal or maximal string that's like in this set, or like is accepted by this function. So, how do we do this? Well, what do we know about like lexicographical comparison? If we have like something that starts with an A, like something that starts with a B, like what do we know about these two strings? We know that this is always going to become before this. Even if this is like a really good string, and this sucks, that's so bad. Like this is still better. So what does this mean for our purposes? This means that if we look at our string, right, and we look at this first character, we ask ourselves, hey, can this be an A? Can we get away with making this an A? I should probably give an example problem. Example problem. We have a string, and we want to reorder it so that no two adjacent characters are the same. And then we want to find the lexicographically minimal such string. So what we can do is we start with an A at the beginning, right? And we ask ourselves, can we complete the string starting with an A? Can we reorder these in such a way that is valid, starting with an A? So we can sort of think of like passing this prefix into an oracle. We have this like mysterious function that tells us whether this is solvable. And in this specific case, this function basically looks at like the frequency array, looks like the maximum versus the sum. That doesn't really matter. What I really care about is this process rather than this process. So if this oracle tells us that there does exist a string starting with this character, then we know that we have to take this character. Because if we don't, then this whatever string we do, even if it's really good, it's going to be worse than whatever like terrible string we end up with here. So if the oracle says, hey, we can start with this letter, we have to now take this letter. It's locked in, and we can go to the next letter. Now we ask, can this be an A? Well, obviously we know that it can't. So we say, no, it's not an A. Is it a B? Sure, it can be a B. It might be really hard for it to be a B, but as long as there's at least one string that lets it start with this prefix, we have to now take that character. We can, I don't know, C, D, C, something like that. And we can fill in the rest of the string. Now, like these problems usually depend on, what is this oracle? Is this like an easy thing to like figure out? And yeah, so there's sort of a variation of this that's harder to see, which is let's just describe the problem. Let's say we have a graph, right? And we want to find the minimum spanning tree of this graph. But instead of adding the weights, we're going to take the bitwise OR. Now, when you see minimized bitwise OR, like min or max, with like bitwise OR, or like bitwise AND, or like bitwise XOR, you should be very suspicious of this. You should always think, is this easy to solve with thinking about this as lex min max? And in this case it is, because since you're just doing the bitwise OR of the weights, the bits don't like leak into each other. If you were to start adding and subtracting numbers, it becomes a lot harder. But since we're just doing bitwise operations, it's very easy to just think of the bits. So let's...
Wait, so define the problem again? Min or spanning tree?
Yeah.
Okay. Just
So similarly to the lexicographically minimal string, we now want to find the lexicographically minimal binary string, because that means that it's the smallest value. So we can look at this first bit and we say, hey, can this bit be a 0? And that's actually, like in this case, that's really easy to like verify, to like check, because for the bitwise OR of a bunch of bits to be 0, this implies that all of the composite bits be 0. So we can look at this. This is a 0, we can take it. This is 0, we can take it. We can take this, we can take this. But this is a 1. We cannot take that edge. So we cross out this edge, we look at the remaining graph, and we ask, does there exist any spanning tree only using these edges? And since it's connected, any connected graph has a spanning tree. So since it's connected, we know that, like the oracle says that this is valid. So we have to then lock in this bit, go to the next one, we ask, can this be a 0? And we can just like erase this edge now. Can this be a 0? Well, we would cross out this edge and this edge, and now it's disconnected because this node is disconnected from the rest. So we know that it can't be that. We set it to a 1, we look at the next bit, that has to be a 1. And then we get our answer. Now, the reason that you can't just do this for any problem where you're doing like lex min, lex max, is because these bits like sort of don't interact a whole lot. They don't like overlap with each other, they don't leak into each other. Although, what is funny is, like, even in an arbitrary problem, like if we go like 0, 1, 0, 1, 1, question mark, question mark, question mark, this is an LR range of binary numbers. So anytime you're doing a binary search, you can sort of think of it as this, but you shouldn't. Okay, are there any questions about any of this? Okay, great. So now we can start talking about some real greedy problems. Yeah. That's good. So we're given the we want to construct a graph on these nodes where we're given the degree of each node. We're given the number of edges that have to be incident to each node. And there's no like self loops, there's no multi-edges. There's at most one per thing. So what greedy would sort of make sense? Because that's where you should start. You should start about like, hey, if I wanted to solve this, is there like an obvious strategy that seems like it should be correct? Like if we look at this one, where would we want to put the edge? Be real. Like be real. Like be real. You want to do the biggest one. You want them to be as small as possible. That makes it easier. That's not a proof. So because in greedies, people say, oh, you shouldn't trust your gut. You should always prove it, but you should trust your gut. You just shouldn't. You should prove it after. So what we're going to do is we're going to prove it. So we're going to prove that. I should specify exactly what the greedy is. The greedy is you can just go through the nodes, and then you always put an edge to the thing with the largest remaining degree.
When you say go through the nodes, are you going through the nodes in a specific
Arbitrary order.
Arbitrary.
Yeah. So like, this becomes 0, this becomes 2. I'll make this 1 instead. And then like, I look at this node, that needs 2 left. So I would go for the 2 and for the 1. I think I messed up the grid. It doesn't matter.
There is an impossible case, so.
Yeah. 1, 2, 3, and then 1, 1, 2, 3, these, and then yeah, this works. Okay, so this is a solution, right? All these degrees match. But if we look at this node, what is it connected to? It's connected to 2, 2, 2. It's not connected to 3. If we were doing the greedy, we would have connected to the 3. But this doesn't say that our greedy is wrong, because there can be more than one solution. What we have to show is that we can always turn a non-greedy existing solution into a solution that would be generated by our greedy. So what we can do is we look at this node, right? We look at this 3, and we say, okay, what would we have greedily matched to? We would have greedily matched to this 3. So we're going to find some node that is not matched to us, that is, A. Some node that's not matched to us, that is greater than some node that is matched to us. Because in our greedy, we would have taken this and not this. And now we're going to show that we can actually swap this edge out for this edge, and then like reform the rest of the graph so that a solution still exists. So since this degree is greater than this degree, there has to be some node that this is connected to that this is not, by pigeonhole, right? So we're going to find that node. In this case, it's this node. So we add an edge here, so we have like an extra degree here. We get rid of this edge here, so we're down 1 here. But then we take this node, we can now get rid of that edge, so now that's the correct degree. Then we add that edge back in, so that's also the correct degree. And we can just keep doing this until we end up with some greedily constructed solution. And then this also works for bipartite graphs. And bipartite graphs, for this problem, I would argue are more important because they do show up more often. They sort of showed up on locals this year, just in a more constrained form. But I'll get to that. 111. Right here. 111. You can see here again, right? We have this 3 that should have been matched to this 3. Let's say like this is A, this is B. A is greater than B. So by pigeonhole still, there has to be some node over here that this is matched to, that this isn't, and then we can make the edge swap. Same argument. And it works. And the reason why this problem shows up more, why it's more important, is because you can think of it in a lot of different ways. You can think of it as, for example, you have a grid, 2, 2, 1, 3, 1, 1. We have a grid, and we want to put like a coin, at most 1 coin in each cell, so that the sum of each row in each column is equal to these numbers. And the reason why this is equivalent is because like each of these numbers is a node on one side of the graph, each of these numbers is a node on the other side of the graph, and then each of these, right? This connects this node and this node. You can put at most 1 thing in each cell, just like you can put at most 1 edge between 2 nodes. Then similarly, I believe the exact locals problem was you have basically like buckets of size 3, and you have like different types of ducks. You have like some number of each type of duck, and you want to put the ducks into the bucket so that no bucket has 2 of the same duck. The locals had specific, like these values as 3, but these can be arbitrary values. They can be whatever. And again, you can see that this is equivalent because you're matching each of these ducks to one of the buckets, so that no 2 ducks here go in the same bucket. So no like multi-edges. And then again, you can just do the same greedy of, take this, match it to the largest ones, and by the aforementioned proof, this always works out. Are there any questions about that? Okay. Okay. Now I'm going to talk about my 2 favorite words. So these two things sort of mean the same thing, but I'm going to use them interchangeably. But this is what I perceive to be sort of a common through line in a lot of these greedy problems, which is the idea of invariants and equivalencies. And I'm going to start with a classic greedy problem called hugging bunnies. Okay, in hugging bunnies, you have basically a bunch of ranges, like a bunch of intervals, and you want to like mark some indices so that every interval is marked by at least one of these like things, and that you want to use like the minimum number of these things as possible. And you're never going to believe what technique we can actually use to solve this problem. It is generating functions. Okay. So what we're going to do is we're going to sweep through. We're going to go until we reach the first end point of a range. And now we're going to look behind us. We're going to say, okay, obviously we have to put a mark somewhere in here, because if we put it too far, then this is never going to get marked. We have to put it somewhere in here. But where should we mark it? You know, we could mark it. Well, we can't really mark it back here, but we can mark it here, or we can mark it here, mark it here, or here. So what's the difference between these? What is the invariant? What doesn't change? Well, since we know that we never went past the end of some range, right? We go through. There's like 1, 1, 1, 1 that we overlap. Now there's 2 that we overlap. Now there's 3 that we overlap. This only increases, because if it decreased, like this range would end. So when we consider like this index, we're never gonna miss a range, but we're like the further ahead we get, the more ranges we overlap with. There's nothing we lose when we go forward. Everything is invariant except for like the number of ranges we overlap, and that strictly like increases. That's arrow? I don't know. It increases. So we can make the argument that we would always just greedily choose the rightmost point, because it's going to overlap with the most things. Now you can't just always do the greedy of overlap with the most things. The specific reason why this works is that the set of ranges that you take are supersets of each other. If I'm here, I can only take this one range. If I'm here, I can take these 2 ranges, but it contains this range. If I'm here, I can take these 3 ranges, but it contains everything that I could take before. It's a strict superset. It's not that it's greater, it's that it's a super, what is the?
Like a superset would be.
I don't know. It's a superset. It contains it. It like, we have A and B, and like B is entirely contained within A, but then A has some extra stuff. There's no reason not to take A. Everything is invariant except for this one like increase. And that specific way of thinking about this is gonna come into play later. So here we go here, and we get rid of all the ranges we intersected with, and we go and we end the range, and we take it, and that works. Okay, are there any questions about that? Great. We're going to talk about a similar problem, which is we're given a sequence of letters, given a string, and we want to construct a string of the shortest length. We're going to say only using like A through D for simplicity, because then we can just do a Z. I don't want to do 26 letters. You want to construct a string of the shortest length that isn't contained as a subsequence of this. It's like A is a subsequence. It's like do. And I'm gonna change up the problem a little bit. I'm gonna change how we think about it. So instead of just choosing, we're gonna choose something with like the minimum length that's a subsequence. That's not a subsequence. We're gonna think about this as Alice and Bob playing a game on this string, where we play as Alice and sort of the problem plays as Bob. Because what we do, right, is we choose a string. We choose like A, D, that's not the right letters, A, D, B, A, D, B. We choose some string, and then, if we were playing as both players, we would just say, oh, it's so hard, I can't find it, it's not there. But Bob really wants to find this in this string. Bob isn't gonna just give up. Bob's always gonna find it. So we're playing against Bob. Now, if I'm Bob in this situation, and I'm starting here, because as Bob, I need to like look for an A, I need to take it. Then I need to look for a D after the A and like take it, and then look for a C. Oh, there's no C. I guess we lose. But Bob has a choice of which letter to take. You take this A or this A or this A or this A. But which one should Bob take?
Leftmost one.
The leftmost one, yeah. Because if I'm here versus here, this I can transition to anything here. But if I'm here, I can transition to anything here, plus a little extra. It's a strict superset of like the transition points, of like the possibilities. Everything is invariant except for something that's strictly better. So Bob's gonna choose the earliest A, then the earliest D, and then the earliest C. It turns out the string isn't there. So now, Alice knows Bob's strategy. Alice knows what Bob's gonna do. And Bob's gonna always choose the earliest one. And Alice is choosing like one of the four letters, like A, B, C, D. So which one would Alice want to choose? Because Alice knows, if Alice chooses A, Bob's gonna pick that. If Alice chooses B, Bob's gonna pick that. If Alice chooses C, Bob's gonna pick that. If Alice chooses D, Bob's gonna pick that. So which of these is the most preferable for Alice?
C.
C, because it's the farthest right. Because if we look at the range of possibilities, much as in the other one, C, we can transition to these, and in any of these, we can transition to all of these and more. But since we want it to be worse off, we choose the one that's a strict subset of every other possibility. Everything is invariant except for this index. So the larger index is always better. So, how it plays out, we look at all our letters, we figure out which one is the farthest right, we choose it, we go there, we go again, D's the farthest right, B doesn't exist, and we win. So the string is like C, D, B. Any questions about that? Okay, now I'm going to talk about. My first way too big. That's fine. I'm going to talk about a problem. This is not helpful. Start at. That's better. Okay. There's like a mailman or something, and there's like letters on some of the cells. I don't know. I should have made this bird bigger. It's fine. It's great. Okay. So there's letters in some of the cells, and there's guys here, and the guys are gonna go out, and a guy is gonna take some path where they only move down and right. They go blah, 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 and they end up here. And they collect all the letters on the path. And if they don't collect all the letters, then they're not gonna go back. They're gonna send a second guy out and take like a second path. And then like a third path to get all the letters. And what you want to do is you want to send out the minimum number of people to get all the letters. So the way to think about it, the way to get into the greedy, is to think, okay, like look at this cell. I've got to get it at some point, right? So, I mean, let's just get it now. Let's get it out of the way. Okay, now like, look at this cell. We might as well, we got to get it at some point. So we might as well get it now. there's a problem, which is that, you know, we could have a second path that goes down and get it instead. So there's this weird variant here. There's this weird like difference here. It's sort of weird to deal with. This crossing. So what we can do is we can do something called canonicalization, and we can get rid of that crossing. Specifically, we can make the argument that if we have two paths and they cross right here, we can actually get rid of that crossing. Because what we do is we take this part of the red path and we turn it blue. And we take this part of the blue path and we turn it red. And now they touch, but they never cross. Now, why is this helpful? Well, if we know that no paths ever cross, then we know that, you know, there's always going to be a lower leftmost path and like an upper rightmost path. Like they're always going to be like well ordered. And furthermore, if we have some letter here that this lower leftmost path doesn't pick up, then we're never going to be able to pick it up. So now, you know, going back over here, you know, before we couldn't say, you know, might as well pick it up now, although some other path might get it. Now we know, oh, we have to get this, or we're screwed. So now that we know paths don't cross, let's go through this again. So we're going to draw out the lower leftmost path. So if we start here, and we're drawing out the lower leftmost path, we know that if we go right, we're never going to get this. So we have to go down and get it. And now we look here. We have to get it, or we're never going to get it. So we go here. And now, where do we go? Because we could go either way, right? We could go, you know, down and over, or we could go over. Now, at first glance, you might think, okay, I mean, this is clearly better. You know, there's like more potential. Like it just seems like it's better. And you'll be right. It is better. But why is it better? The set of things that this can go to is like, and the set of things that this can go to, well, it could go down and then go to everything this could go to. Or it could not go down and go to a bunch of other stuff. The set of things that this can go to is a strict superset of the things that this can go to. Everything is invariant except for this thing, which is strictly better. You know, the set of letters we pick up is invariant, the column we're in is invariant, the only thing that changes is the row, and the higher row is always strictly better. Or loosely better. It's like, it doesn't matter. If two things are equal, then, you know, you can pick this, you know, without laws of generality. So, you know, greater than or equal, strictly greater, same thing. They're in all mathematical cases, greater than or equal and equal and greater, they're all the same thing. This is my fun fact of the day. So we go here, we're like, okay, do we go down? No reason. Do we go down? Gotta. Bang. Okay, do we go down? Don't wanna. Go down? Don't wanna. Gotta. Don't wanna. And then we go, don't wanna, we gotta. And then we do the greedy. Greedy. Any questions about this?
I was just slightly confused about the, so like, we're allowing paths to touch, they're also allowed to coincide for a period of time, right?
Sure.
So, when we were doing like the canonicalization, in order to like say something about the points that are like below one of the paths, couldn't we just have a path that just follows that and then goes to it? Or is that what you were talking about with the like one is strictly better, so it like doesn't matter?
Well, okay. Like if we have this point here, and we know that it's below this like lower leftmost thing. Even if this like coincides the whole way, you know, we can't go down because we know that because that would still be a crossing.
Okay, I see.
So we can like in our mind we can pretend this is like epsilon further this way. even though it's like the same path, but like if this and this coincide, and then this breaks off, and then they come back together, and then they coincide, and they coincide, and then this breaks off, it goes down, and they go back together. Yeah, there's a crossing here, and we can take this and we can swap them out so that this is blue in both cases.
So by crossing, you're effectively more so just talking about like one being above and the other one being below.
Yeah.
Okay.
Yeah.
But they never even gonna like match. Never.
Hmm?
They're never gonna be in the same path.
They
They really.
they could be, because if
Yeah.
like even here pigeonhole, you know, like these, like this has to probably be used by multiple.
Yeah, but like at the beginning, yeah, but at some point it needs to like diverge.
Yeah, it's gonna diverge at some points, and then when it diverges, this will be lower and this will be higher. And then like when they converge and diverge again, you can do the swaps and you can just always make sure that this is lower. Any other questions? Yeah.
So like the actual implementation of the grid is like
Yeah, yeah.
you start at the start, and then like always go right unless there's a thing in the current column that you need to go now for.
Yep. If you gotta get it, get it. If there's nothing to get, just go right. Good. Okay. We're gonna talk about weighted balanced bracket sequences. I'm not gonna throw that one because it's not that bad. I don't have a contingency plan. Whoa! It's gonna stop working in 8 minutes. That's not. Other way. Okay. We have a sequence of numbers, a sequence of like weights. And then at each index, we're gonna place an open parenthesis, or a close parenthesis. And we're gonna go, whoa, 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 whoa. And you have to make sure that by the end, it's balanced. Balanced meaning, like if we think about this as like, you go up by 1, and like this, you go down by 1. And I'm doing this because this is, I think, a really good way to think about balanced bracket sequences in general. Is you start at 0, this is 0, open parenthesis, you go up, close parenthesis, you go down, do. You have to make sure that you never go negative. And also you have to end it at 0. And then you want to maximize or minimize, doesn't matter, the sum of open parentheses or close parentheses. We're gonna say maximize open, they're all the same problem. Yeah, max sum of open, so I don't forget. That's a C, whatever. Okay,
And like a closed parenthesis is just, it doesn't do anything.
yeah.
Okay.
Like I'm sure you could have it be like negative weight. You could turn it into this problem. Like every problem of this type is equivalence. Equivalence. Okay. So, what do we know? What do we know about balanced bracket sequences? We know that every prefix, let's say like size 5, every prefix has to have at least as many open parentheses as closed parentheses. Because if this, it's a weird symbol. If this exceeded this, if this was less than this, then you would go like, this is like 3 and this was 4. Go like up by 3 and then like down by 4 and you would be negative. We know that every prefix has to have at least as many open as closes. So, look at this prefix of size 1. What does this have to have? This has to have at least 1 open parenthesis. Now look at this prefix of size 3. How many does that have to have? It has to have at least 2. And then this has to have, size 5 has to have at least 3. Then this, size 7, has to have at least 4. So, how we can think about this is, we're gonna place an open parenthesis somewhere in this range. And now, this is gonna decrease each of these by 1, because it's incurred. Let's say, yeah, we put 1 in this range. It's gonna decrease each by 1, so there's 0 here, 1 here, 2 here, 3 here. Now we're gonna look at this range. We have to have at least 1 more. So, we're gonna place 1 in this range. There's one here, exactly one, there's one here, then we're gonna place one here. This is gonna decrease this by one, this by one, this by one. Now we're gonna place one in this range of size 5, and then we're gonna place one in this range of size 7. So we're doing these things in order, where we look at this range of size 1, we place an open parenthesis. Now we look at this range of size 3, we place it somewhere we haven't placed it before. Let's say here. Now we look at this size 5, we can put it here, we can even put it there. And now this size 7, we put it, say, here. And now we know that this has to be a valid balanced bracket sequence. And this also like encompasses all possible balanced bracket sequences. So, any questions about that so far? Okay. So now what we're going to do is we're going to place an open parenthesis in this range. I mean, that's easy. There's only one place to do it. Now we're going to place one in this range, right? You know, it could be here, could be here. We don't know. But now, you know, once we've placed this, every range after it strictly contains this range. They never like intersect the range. They never differentiate these two. These two are always equivalent. They're completely equivalent. They can't be differentiated by anything other than their value.
Why are you only drawing the odd size ranges? Like, is that just for? Like, do you know?
Well, I mean, you could draw it, but like, this is,
Equivalent? Oh yeah, I guess.
well, like if you have one, you have to put one there.
Yeah.
You have two, you also have to put one there. So
Okay,
like,
okay.
it's the same thing.
It's
Like
like this
subset, so
subset,
like the
yeah.
subset is more required, like,
Yeah. Okay, so now when we look here and we're deciding which one do we do, we think about how is this going to impact our future, and we know that this and this in the future are going to be completely the same, other than their value. So we might as well pick the one with the better value. We can greedily choose the one with the better value out of these three. And now when we look at this thing of size 5, right? We could do this, we could do this, we could do this. But going forward, these three will all be equivalent, other than their value. So again, we can just pick the one with the best value. And then we look at this of size 7, we pick the one with the best value, and we're done. So the whole reason here is that these like ranges that we're allowed to place things in are supersets of each other. Is there any questions about that? Yeah?
Is it like the complete range, or is it the range after the previous range?
For what?
For picking.
You pick anywhere in this range, because you know that place one here, you place one here. There has to be one in this range that you haven't placed before. So like this, they're all equivalent going forward. So you're not just picking like out of these two, you're picking out of this entire prefix that you haven't placed before. Any other questions? Okay. Okay, we're going to talk about greedy undoing. What is this problem? That's what this problem is. So what I'm going to describe, I think you could actually use to solve this problem that I just described, but I think both strategies are worth knowing. So you have some like potions or something, +4, -3, +1, -8, -2, -7. And then you want to you're going to go through them in order. You're going to either take the potion, or you're going to leave it. And like you start with 0, and then you like this gets incurred to your score, and you have to never go negative. So it is sort of similar to the balanced bracket sequence, right? Like with balanced brackets, like +1 or like -1, and they have weights. But here it's +x -y, and then they have weights of 1. So again, we're going to think about this graphically.
You're trying to maximize the number of potions?
Yeah, maximize the number of potions you take, while making sure you never go negative. So like, let's say,
And you take them in order.
yeah. You go through them in order. So like +4, -3, +7, -6, +1, -5. I don't know how that would work. You have this. So we're gonna go through, we take this, 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 we take this. We must have done something wrong, because we're now negative. So obviously we're never gonna not take a positive, because a positive is only good. It only makes our value higher, and it only makes our like count higher. So we only care about the negatives. Now, what happens when we don't take a negative versus taking a negative? If we were to have not taken this, what does the rest of our graph look like? It looks like this, and then this, and then this, and then this. And you'll notice that at every point, our value is at least as high as it was before. But specifically, what's notable is that we never went negative before this point. So if we only increase things, we will never make it, like, we will never, like, retroactively make it negative whenever we get rid of one of these. So, like, if we got rid of that, it wouldn't have gone negative back here. If we get rid of this, you know, it wouldn't have gone negative back here. And then if we get rid of this, it wouldn't have gone negative back there. So it turns out everything behind this point is invariant. It will never, like no matter what weird path we take, since we know it will never go negative, we don't actually care about it. The only thing we care about is, you know, how negative these are, because that impacts our final, like, value. So now, if I'm here and I have, like, this thing is like pretty negative, this thing's really negative, and this thing's fairly negative, which one would we want to get rid of? Yeah, we want to get rid of the thing that would cause our like value to be highest, because that's the only variant. Everything else is invariant. So like if I were to take this, it would be here. If I were to take this, it would be here. Like this is always strictly the best thing, because that's the only piece of information we have. Everything else is like, it was valid, so it's valid now. This is the only thing. So what we can do is we literally just keep track of the negative things we have, and then anytime it goes negative, we get rid of the most negative thing and like retroactively change what we did into being that. So like we go like do and do and do. Now there's like super negative. We just placed this. We're gonna just like immediately get rid of it because this is the most negative thing. And no matter what we get rid of, nothing back here will ever dip below. It only goes up. So like if we get rid of this, you know, all of this turns into this. It's like strictly better. That's invisible. I swear that was a good one. All right, well, bye. Okay, are there any questions about this? Great, cool. Next problem. Okay, this is a classic problem. This is a classic exchange argument problem. I think I'm going to erase these. I don't think I really talk about those much anymore. Exchange arguments. We're going back to the iconic balanced bracket sequences. So we're given a bunch of not necessarily balanced bracket sequence like strings. What we want to do is we want to concatenate them in some order so that like the resulting string is balanced. And we have to use all of them. We can't like skip any. So we order them arbitrarily. We get it together. It has to be balanced. So let's go to our best friend, graphical balanced variant, mountain, whatever. So like right here, floor, So looking here, since we're never gonna like split this up or like rearrange the things in here, there's actually very little information that matters. Obviously we care about the start, and then we care about the end. Well, the start's always gonna be 0, so really we just care about, you know, that's an A, not a delta. We care about that difference between them. Now, is that all the information that matters? No, because like we have this sequence, we go like down, down, up, up, but like this sequence, we go down, up, down, up. These are different because if we went like up and then down versus like up and then down, this wouldn't be negative, but then this would go negative. So we care about two things. We care about this difference, and then we also care about the lowest point that it gets to. So we can turn into these balance bracket sequences into like a pair of values where we have the amount that it changes by, and then we have like the how high it has to be at least. And we have like this is just like horizontal, and it has to be, you know, at least this high. And then we have like this goes down, and it's just gotta be there. We want to rearrange these to make it a balanced bracket sequence. So let's forget about like the floor stuff for now. Let's just think about the vectors. If we go up, 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 down, and then we go up again, and then we go down again. We have some place where it goes down. So we have some wiggle waggle in the middle. Like this can be anything. And then we go up, and then we go down. We have this, we go down, followed by some time later, we go up. Now, is this optimal? Or can we swap these? Because if we swap these, if we put this here and we put this here, it turns into, we go up, and then wiggle waggle, and then we go down. And we can see that at every index, at every point, just like in the other problem, it is at least as good as it was before. So we might as well swap them because it's going to either get better or be the same. So what does this mean? This means that there can be no down before an up, i.e. we can keep swapping until every up comes before every down. And now the only thing left is like the horizontals. We can make a similar argument where if we go up, if we go horizontal and then up, we can just swap these. And it will still also be at least as good at every point.
Wait, are you saying you can't, because like if you have a guy whose delta is up, but his mean is super down, like what, like the argument that I think you're trying to make is like some plus the min.
We don't care about the min, because as long as all of these ranges go up, they become strictly more possible.
Yeah, but like you said, like a range that goes up will always go before a range that goes down.
Yeah.
But how is that accounting for like a range that delta's up but has a super large minimum?
That's still true, though it will come before everything goes downwards.
Okay, if we go up, then we go down here. Waggle, waggle, waggle. We go up, and then we go down, whatever. Right? And this has some delta. Some min. And then we take this range, and we put it here. This min is now strictly higher than it was before. And the same with this. This min is now strictly higher than it was before. And everything in here, they get shifted up. Their mins are also strictly higher than they were before. So everything is strictly improved in terms of their actual value, their min value, everything goes up or stays the same.
Yeah, but the way of building this, you will need to take the one that is the biggest delta, but you can place there. It has like a mean that you can place. Doesn't matter what is the mean as long as you can put it. Like the order of the ups, it will change. Like they will come before the down, like they will change.
Yeah, so we're going to talk about the order of the ups now. All we've done is we've proven that the ups come in all before the downs. And similarly, I don't know if I drew this out, but you can, I'm just going to go quickly. We can prove that the ups all come before the mediums, and the mediums come before the downs. So we have one chunk of ups, one chunk of crosses, and one chunk of downs. So now, we know that every up we take only improves our status. So we like look at our set of things, and we're like, hey, if they're an up, even if it's like not that good, but if we can take it, we might as well take it. There's no point in not taking it. So we'll take it, and then we'll look, is there anything else we can take? We might as well take it. We might as well take it, might as well take it. There's no like non-benefit to taking it. And if we can take them all and get all the way up here, then we're good. Then we look over here, everything's symmetric, we can just do it in the other direction. And then we look here, this height is fixed, So we take them in any order, like no matter what order, it's still gonna be the same height, like nothing matters. So we just have to make sure that they're the correct height. Any questions about that? Okay, we can do that maybe quickly. Okay. One less problem. We have a list of strings, and we want to reorder them and concatenate them into one big string so that the resulting string is lexicographically minimal. So, the greedy that comes to mind is just sort them lexicographically, right? Like that kind of makes sense. Does that work? Let's see. A, B. Well, if we have like AB and like AC, we can obviously see that the AB has to come before the AC. It's lexicographically better, it's obvious. But if we have a case like this, A and AB, is it obvious that this has to come before this? Well, it happens to, because AAB is better than ABA. But if we had something like Z and like ZB, then like ZZB versus ZBZ, this one is actually better. So how do we compare them? Because what we're doing right now is we're seeing if we have two adjacent strings, how do we know which one comes first? Well, we already did it. We just make the two strings and see which one is better. So what this does is, if we order our strings in some order, and we say that this is better than this should come before this, like locally. This comes before this comes before this. This means that it's optimal, right? No. Because you could have like an improper ordering. You could say like A is better than B is better than C is better than A. We have to prove that this relationship is transitive. If we can prove that it's transitive, then this is sufficient to prove that the entire thing is optimal. And we're going to prove transitivity with the following. We're going to pretend that the letters are not letters, but they're like digits, right? So we have, let's say 1, 2 here, and like 1, 2, 1, 3. So, which is better? What do we do? Well, we're gonna, let's say this is A and this is B. We're gonna concatenate A to B, like 1, 2, 1, 2, 1, 3. And we're gonna compare it to 1, 2, 1, 3, 1, 2. Now, how do we figure out which one is lexicographically better? It's the one with the better number. It's the one with the higher value, because those are the same. So if we find a way to construct this number from these two numbers, and this number from these two numbers, we just compare their values. So, what is this value? This is the number of digits in A, this is the number of digits in B. So we take A times 10 to the B, 10 to the size of B, plus B. We compare that to B times 10 to the size of A, plus A. So we compare these two things. And I should have written that in the line. A times 10 to the size of B, plus B, greater than B times 10 to the size of A, plus A. Now, there's like A's and B's everywhere, but what we can do is math. We can, subtract A and B from each side. This is minus A, this is minus B. Then we divide each side by A and B. So we, divide out the A there. We get divided by B. Divide out the B there. We get divided by A. Now we can see that this side only has B's. This side only has A's, which means we can just take this number, turn it into a different number, and then compare the numbers. And obviously, comparing numbers has to be transitive. So now we know that this is transitive, and we know that this is less than this, this is better than this, this is better than this. So the whole thing has to be a proper ordering. And then it works. Any questions about that?
There will be a quiz.
There will be a quiz. It's Saturday practice. Every problem is greedy. Oh, yeah.
Can we just sort by those values that we get now?
It would be hard to because these strings are going to be really long, so you would have to store the value. Like hypothetically, you could, but in practice, I should talk about practice because this thing does show up. In practice, the way you should implement this is like one of two ways, and one of them is really easy, and one of them is bad. Because like when you're comparing two strings, but and but, you need to like A and B. You need to compare A B to B A. How long does that take? That takes like size of A plus size of B. I think it's actually max of these. But max can be slow. So there's two things you can do. You can use like z function and whatever to like make sure it's min instead, or you can just shuffle the strings and it usually works. Like shuffling the strings, it'll just run fast. That's just a little tidbit in case this shows up ever. All right, now we're gonna take -1 minute to talk about 0, 1 on tree. It's a greedy problem.
Is that the end of the lecture?
I mean, the time's up, so I would assume so.